Right, here we have an exercise. You need to show, again, using mathematical induction, that 1 plus 2 plus 3 plus 4 all the way to plus n, okay, is equals to n times n plus 1 divided by 2 for integers n greater equals to 1. Okay, so recall our first step is to identify a property. So property Pn is 1 plus 2 plus dot 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 plus n equals to n times n plus 1 divided by 2. This is copied from here. Alright, okay, this is our property. Our next step is to prove the basis step. That means we need to identify what is the smallest value for n. Okay, given the question n greater equals to 1. So in other words, we need to prove P1. Okay, prove that P1 is valid. So how do you prove that P1 is true? Okay, you see Pn is actually a equality, right? It's a equation. We're saying that the left side equals to the right side. So when we want to do prove P1, we are telling people that, okay, if n equals to 1 here, okay, and n equals to 1 here, they are still equal. Okay, but you notice that our left hand side is actually a sum of terms, right? Okay, so when we're talking about P1, we are talking about just one term here. So when n is 3, let's say n is 3 is 1 plus 2 plus 3. When n is 4, it will be 1 plus 2 plus 3 plus 4. What happens when n equals 1? When n equals to 1, we only have one term, so our left hand side is 1. Okay, and our right hand side, we substitute 1 into where n is, so we have 1 times 1 plus 1 divided by 2. So right hand side, we need to do some simplification. You have 1 times 2 divided by 2 end up equals to 1, okay, which is actually equals to your left hand side. So you have proved the basis step. Okay, next is the inductive hypothesis, where we make an assumption. Okay, so in this case, we assume pk is true. Okay, again, k, if you sub into our left hand side, it will be 1 plus 2 plus 3 plus 4 all the way to plus k. Okay, and our right hand side will be k times k plus 1 divided by 2. So because this is an assumption, there's no need for you to prove that they are equal, but we will make use of this assumption in our proof for pk plus 1 at a later stage, right? Okay, so we are at step 3b, where we need to prove pk plus 1. Okay, show that pk plus 1 is true. So in other words, we need to prove that 1 plus 2 plus 3 plus all the way to k plus 1 is equals to k plus 1 times k plus 1 plus 1, which is k plus 2 divided by 2. Okay, so same thing, mathematical induction. Just now we mentioned we always use the same trick. We try to manipulate the left hand side to look like the left hand side of our assumption. Okay, so left hand side is 1 plus 2 plus and so on all the way to k plus 1. Okay, we purposely include the second last term. Okay, include the second last term. So before we can hit k plus 1, our second last term is k. Okay, the significance of this is that this first few terms here from 1 all the way to k actually forms the left hand side of our assumption. So our assumption, we can then use it here to do a replacement. Okay, we use the right hand side of our assumption and we replace this part here. So you have k times k plus 1 divided by 2, k plus 1. Okay, once again, if you were to pause and inspect, you will notice that this left hand side now, okay, we are almost having the same form as our right hand side. Okay, so just a little bit more, you'll be able to prove that it's equals to the right hand side. Okay, once again, we are faced with fraction addition, so we need to make sure that the denominator is the same. So for this term, we multiply by 2 and divide by 2. Okay, so that they have the same denominator and we can add them together. Okay, so we add the two fractions together. You have k plus 1, k times bracket k plus 1 plus k plus 1 times 2. Okay, at this stage, there may be a temptation for you to multiply the k into the bracket and multiply the 2 in the bracket. The problem with doing this is that once you multiply it, you have k squared. And if you notice our answer here, there's no k squared. Okay, so there must be a easier way for us to handle this now. Okay, the easier way is actually this. If you notice this term here, we have a bracket k plus 1, and this term here, we have a bracket k plus 1. So this is actually the common term. We can take it out. Okay, so we take out the common factor k plus 1. Okay, what is left from the first term is k. What is left from the second term is 2. So you have k plus 2, right? And the whole thing is divided by 2. So this actually is the same as our right hand side here. So it's equals to the right hand side. So you have proof that pk plus 1 is true. Okay, so finally end off with a conclusion. Since we have proven basis and inductive step, Pn is true for n greater or equals to 1.